Good afternoon, everyone. So we are starting this webinar today. My name is Rez Mani. I'm an application scientist for Allied Scientific Pro. And today's webinar topic is more on laser cleaning and laser ablation. It's mostly focusing on laser cleaning, but I'm going back and forth between laser cleaning and laser ablation. So there's some difference between the two, which I'll explain later. So this webinar is being recorded and will be sent to you later. And my email is mentioned here at the bottom. So if you have any questions that you want to discuss, you could either ask me at the end of this webinar. We have a Q&A session, or you can email me and I'll try to answer your questions. This is the third or fourth time that I'm doing this webinar, and every time I try to improve on the presentation, add some stuff, make it more clear. So hopefully its quality has improved compared to the previous times. And so let's begin with this laser webinar. So the outline of the talk is, first, I'll talk about introduction to laser ablation, and then laser cleaning basically is a subset of laser ablation. So laser ablation is more general. It includes many different aspects such as cutting, drilling, scribing, and then cleaning is a part of laser ablation. So that's the difference between the two. Then I'll talk about laser medium. So what are the different types of lasers that exist, and what is the medium for it? Some of them could be gaseous, and some of them could be solid state lasers that are used for cleaning. Then types of lasers used in laser ablation and cleaning. Then we would compare laser cleaning with some other competing surface cleaning techniques. Such as sand blasting, water jet blasting, chemical methods, and things like that. Then we would go a little bit into the physics of the laser ablation and its dependence on material properties and laser parameters, and how we can choose a proper laser for a proper material. There's some physics involved there. And then we would compare different pulse width lasers, the femtosecond, pico-second, and nanosecond regime. And we move on to application of laser ablations, and I've singled out 3 different applications here: cleaning of artwork and historical monuments, laser ablation for removing paint from aircraft, and laser ablation for nuclear decontamination. And we will also have a number of videos that we will show throughout this presentation to make the concepts more clear. And at the very end also, there are a number of videos that shows the Allied Scientific Pro's laser cleaning system in action. And we finish with some conclusion. So what is the principle of laser ablation? Laser ablation is a process through which a high power laser is focused on a surface and removes material from it. So it would cause production of a large amount of heat on the surface, and it will vaporize material from the surface. And this could be used from laser machining, laser cutting, paint, or contaminant removal, drilling, scribing. Now, most of the lasers that are used for laser ablation are pulse lasers, but you can also use a CW laser. This talk mostly focuses on pulse lasers. You have more control of parameters in case of pulse lasers, because you could play with different parameters such as pulse width and and repetition rate, whereas in CW laser you just have a continuous wave. So you can change the power, but there's not much control. So maybe better to use the pulse laser. So here we have a laser ablation video. It's an animation that shows how the laser ablation takes place. So let's take a look at this. So you see that the material is being irradiated by a laser beam, and all these atoms and particles are being vaporized, and they just are ejected into space. So this is like an animation that shows how laser ablation operates. Or depending on the heat that is generated, sometimes a plasma is created. We'll talk about that plasma, but if the heat is not strong enough, it just vaporizes the material. Okay, so this was a very quick video that showed that. Okay, so let's move on. Principle of laser ablation, more on that. So when the laser beam irradiates the surface, it either evaporates the surface at lower energies or will form a plasma at higher energies. In fact, I'm going to move to the third point. If it creates a plasma, then this plasma will also have like an emission. And one can study this emission using spectrometers and understand or find out what is the composition of the material that is there. And this is the basis of the technique called laser-induced breakdown spectroscopy, or LIBS. So shine a very strong pulse laser on a material and create a plasma, and then look at the emission from the plasma. And that is the laser-induced breakdown spectroscopy, which is a much better technique than using strong acids to dissolve the material, and that requires sample preparation. So this is one application of finding the composition of the material. Now, this also could be used to remove thin coatings from a material surface, such as rust, paint, oxide, thin films, etc., and therefore laser cleaning. And as I mentioned before, I emphasize again, laser cleaning is a subset of laser ablation. Laser ablation is more general. The depth over which the surface is ablated depends on the material properties and also on the laser properties, such as wavelength, pulse length, and pulse energy. And we will go over these parameters that are important for laser ablation, both for laser and the material later. And we would just examine like what are the factors that we have to look at when we are having a particular application. We want to choose a particular laser. Total amount of material ablated from the surface per pulse is called ablation rate, and this also depends on laser beam scanning velocity. So there are other parameters that are also important, such as the pulse repetition rate and energy, but also the beam normally moves on the surface using some galvo system. So how fast it moves also depends or affects the ablation rate, how much material is being removed per second. What are the important parameters for laser ablation? As far as the laser is concerned, there is wavelength is a number one parameter, and some wavelengths are heavily absorbed by some materials and others are reflected. So depending on what material you want to use, you want to be careful about choosing the proper laser. For example, plastics heavily absorb in mid-infrared, so suitable for CO2 lasers. Organic material also have high absorption in mid-infrared. Metals better absorb in near-infrared. So if you want to cut a metal, it's always better to use a near infrared than far infrared and mid infrared. But metals don't have that much absorption for plastics. Sorry, the near infrared laser uh, basically plastics don't absorb too much near infrared. They absorb mid infrared more than near infrared. So this is one parameter. We'll go over it later on. I'll show you a curve later. Then the pulse width comes into picture. The depth of the ablation may depend on the pulse width, and that is defined by the thermal penetration depth. And I'll show you some equations later. So longer pulse width will have more penetration depth and require higher energy per unit area to ablate the material. So after a certain pulse width, you have to be careful to basically adjust the parameters and what pulse width you're choosing, because certain transitions take place. So the heat is penetrating the material more after a certain pulse width is exceeded. So I'll go over that later. Pulse energy, the rate of ablation will be higher with higher pulse energy. Of course, when the energy is more, the rate of ablation would increase. Beam shape, this defines the size of the imprint by the laser. For laser machining, must be small, but for paint removal, it could be larger. It could be a line a few centimeters in length, for example. If It also depends on something which is called the diffraction limit, because if the wavelength is larger, you can't focus the beam to a very small spot. So, for example, CO2 laser, which is at 10 micron, cannot be focused to a small spot as compared to YAG laser, which is at 1 micron. So the longer the laser wavelength, the harder it will be to focus it to a very narrow spot. So that also relates to the application. If you're looking to cut something or remove very small features, then you might want to go with a shorter wavelength laser. That will give you the smaller beam. Repetition rate, higher repetition rates will increase the depth of ablation. So that affects how deep you can go. And the depth of ablation is related to that. So now let's a little bit talk about the laser medium and the principle of operation of laser. And this is some basic knowledge. I want to show you a video. So lasers normally have a medium which causes the lasing. This medium normally is a gas, or it could be a crystal, a solid crystal. And so in this example, I'm showing you it's a gas that we are looking at, and then some of the atoms of this gas, they can get excited if you pass an electric current, for example, through it. So that's called the gas discharge. You pass a current, and the electrons will hit these atoms and put them in the excited state. So these bigger circles you see here are excited atoms. The smaller one are unexcited. They're not excited. So once an atom goes into the excited state, then the electron comes back to the lower level immediately, and it generates a photon, and that's called the spontaneous emission. But if an atom is in the excited state and a photon that is generated by a spontaneous state emission hits that atom, then it will produce a clone of the same photon. So that's called the stimulated emission. So two similar photons will be traveling after one hits the atom in the excited state and generates the stimulated emission. And this way you could multiply number of photons that are clone of each other, And if you put two mirrors, the laser medium is normally between two mirrors, then they go back and forth, and then this gets amplified basically. And once the amplification takes place, you get this beam that has identical photons. This is a coherent beam. All the photons have the same wavelength, basically phase, direction, and all parameters are similar. And all you need is to make one of the surfaces, one of the mirrors, to be partially reflecting. The other is fully reflecting. One is partially reflecting, and then the laser beam emerges from that side. So let's look at this video and then see how this works. So here you see this is the atom that is excited. So the electron is moving to the upper, and here gets excited, and this is a spontaneous photon that hits this, and then it generates another one. This is a stimulated emission. And you can see that if you put mirrors, and these are all the atoms that are in the excited, so this stimulated emission goes back and forth between the two mirrors, and a coherent beam is generated. And then if you put a hole, or if one of the mirrors are partially reflecting, then you can get the laser radiation coming out. The resulting photons are identical. They have the same energy, which gives the same color and a unique direction. This is how a laser works. So this was basically just the basic introduction to what is the importance of a laser medium, because we'll be talking about this later. So types of lasers that are used for laser ablation. And again, I said focus will be on pulse lasers. So there are many different types of lasers, all the way from UV to mid IR. So let's just start with from the left. You have the excimer laser, which emits in UV, in ultraviolet. It's a nanosecond pulse. Normally, it has a really low repetition rate, about maybe anywhere from 10 to 100 hertz. So this is lasing action is formed by this excited molecule, which could be argon fluoride, xenon bromide, xenon fluoride, and each one has its own particular wavelength of emission. So you can see it in this chart: 193, 282, 351. So the medium of lasing in this case is a gas made of these excited molecules. Notice that argon, xenon, they're all noble gases, so normally they don't interact with other gases, but under certain conditions they form a temporary bond with the halogens such as fluorine, bromine, and then they lase. So these lasers are very expensive, and they're normally used for applications such as photolithography. UV lithography is a process used in microfabrication to pattern parts of a thin or bulk of a substrate. Usually in the semiconductor industry, these are used to make a pattern on the circuits. Because of the short wavelengths, it has a high resolution, and you can focus the beam down to a very narrow size, and therefore cut very small patterns or form very small patterns. Next, we move to a CO2 laser. This is another gaseous laser. It is in mid-infrared wavelength, a pulse width of nanosecond. It could also come in a CW form. Normally, it's very much used in the industry for cutting applications. You can get kilowatt CO2 lasers. You can also use it for laser cleaning. We'll come to that later. Its wavelength is 1.6, 1.06 micron or 10,600 nanometers, pulse width about 100 nanometers, the gaseous medium. The pumping method is gas discharge, similar to excimer laser, which means that you pass a current through it, and then you can excite the molecules of the gas. It needs some cooling because it generates a lot of heat. And next, we move to neodymium YAG laser, uh, which is a very popular laser in many different applications, including laser ablation and laser cleaning. It also used in LiDAR systems. A pulsed laser is a pulse laser, nanosecond pulse width. Its wavelength is in near IR at 1064 nanometer. Now, the medium of operation here is a crystal called, it's a YAG crystal, yttrium aluminum garnet crystal, and it's doped with the neodymium. Neodymium. So the lasing takes place in this crystal, and the pumping of this laser is usually optical. So you could pump it with the laser diode or with arc lamps. And the other great feature of this laser is that you could use harmonic generation. So you put harmonic crystals and double the frequency, which would half the wavelength. So for 1064, you can also get 532 nanometer and 355 nanometer, and even quadruple to 266 nanometers. So you can generate multiple wavelengths if you use harmonic crystals. And then we would move to Ti Sapphire laser. This is a near infrared laser which is tunable anywhere from 650 to 1100 nanometers. And in the pulse mode, basically its pulse is very narrow, femtosecond laser, 10 to the minus 15. And it is used for laser machining and semiconductor research. Utilizes this laser. This laser, I would say, very expensive, the Ti Sapphire. And one reason for it to be so expensive is that it has to be pumped using an argon laser or another green laser. So the pumping makes it more expensive, and then it's tunable also. Similarly, excimer laser is very expensive, but the CO2 and neodymium YAG lasers are more affordable. But then there are pros and cons for each one that we'll go through later. You also have the fiber lasers, another type of laser which is becoming very, very popular. And actually, Allied Scientific's laser is based on the fiber laser. And in this case, the medium of lasing is a doped fiber. So it's doped with ytterbium, erbium, thulium. These are all rare earth elements that are mixed in the material of the fiber. And instead of having mirrors on either side, you have this thing called fiber Bragg gratings. So these gratings are scribed inside the core, and they reflect only a certain wavelength. So the radiation goes back and forth, gets reflected and gets amplified. So these fibers have great flexibility to reach hard to reach places. The pumping is through diode laser, and they're more economical than CO2 lasers. And basically, they have a lot of advantages such as high pulse energy, high average power, good beam quality, and variable pulse length. So let's look at what is laser cleaning. So use of high power pulse lasers to remove materials from a surface helps to clean the surface. Lots of times surfaces are contaminated with nitrate and sulfate, especially in outdoor environments for historical monuments. You get all kind of pollutions are deposited. Uh, so absorption of laser radiation causes rapid heating of surface contaminants and generates a shock wave and vaporizes the contaminants. Some examples are historical structures and removal of paint in aviation industry, which we'll go in detail later. Fiber optics is sometimes used to direct the high power laser towards the surface that needs to be cleaned. So this flexibility of fiber optic is very important, and this is one reason near infrared lasers are used so often, because fiber optic has already been developed for these lasers for communication. Telecommunication uses fiber optics in compatible to near infrared. So, but when you go to mid infrared at 10 micron, the fiber optics are not so readily available. They're more expensive. And so that gives an advantage to near infrared over mid infrared. Uh, Now, there is also different physical effects, mostly for near IR is photothermal. So it's all thermal effects, but for UV lasers, they're photochemical. So the laser actually dissociates the molecule. So in certain applications, it may be really required to dissociate the molecule. Just the thermal evaporation may not be enough. So let's look at a video of this laser cleaning in action. This is a system by Allied Scientific Pro that you see on the right side at the bottom. And here is, like, you see some optics. There's a galvo system, and this is a whole laser machine. And you see that how it would evaporate some metal. So let's look at this video. So here you see the beam, which is linear, and it's a few centimeters long, and it's a near infrared wavelength, so you can't see it, but you could just see the plasma that is generated when it hits the metal and just removes the rust. And this pipe here sucks all the ablated material, so keeps it clean. So this way you can do the cleaning of rust in on the surface of metals. Okay, so let's move on. Yes. So next would be the fiber lasers are becoming more popular in the industry. And here is a chart that is from the Industrial Laser Solutions for Manufacturing, a special report published in 2015. And you know, several types of lasers are listed here: carbon dioxide, solid state, fiber. And you can see in 2015 there is an increase in usage of fiber lasers. In fact, fiber lasers showing a 13% increase in revenue as compared to solid state. That's gone down by 3%, and carbon dioxide has gone down by 1%. And there are other lasers, maybe Ti Sapphire laser could be listed under other, but their revenue has increased as compared to 2013 and 2014. And you can associate that with flexibility and ease of operation of these fiber lasers that make it easier as compared to other types of lasers. So now let's look at some other methods of cleaning surfaces. What is special about lasers? This is a question. Why can't we use other methods? So some of these pros and cons are shown here. There are other methods. Mechanical abrasives is shown here on the left, where you actually put this rotating disc and physically remove the material through friction. And then you also have the chemical method, where you apply chemical to the surface and wait for a few minutes, and then some chemical reactions takes place, and then you would actually scratch the material off the surface. And you also have dry ice and sand blasting, where you have these nozzles and you shoot dry ice and sand blast sands basically at high pressures towards the surface. You can also have water jetting, same principle, high pressure water jetting or dry ice or sands. So what are the disadvantages of these methods? First of all, they create a lot of pollution and debris, which is hard to be cleaned. It's not healthy for the environment. As you saw in the laser cleaning, there was a suction pump that would remove all the ablated particles and keep it clean. But in this case, you have a lot of contamination. Secondly, it could damage metal substrates underneath, especially chemical methods and mechanical abrasives could damage the metal substrates. For example, in case of aviation industry, process cannot be automated. Usually you have an operator that has to do it by hand. And it is pretty noisy, normally in the noise level 110 to 120 dB, which is as loud as a siren. A laser cleaning acoustic noise level is about 76 dB, which is the same sound level as a crowded restaurant. So these are some disadvantages of these other methods. Now, what are advantages of laser cleaning? First of all, it's non-contact. It's only light that is hitting the surface. There is no solid to solid contact. A low environmental impact. There's no chemical waste. Selectivity. Certain parameters such as pulse width, wavelength, repetition rate can be tuned to suit some material better. A localized action, it only operates where the beam is pointed, whereas in a chemical method, for example, the chemicals could spread to other parts. Preservation of surface details, you can focus the beam down to a very small spot and work on the surfaces that have a lot of fine details and clean them. Controlled removal, only a certain control thickness can be removed. You can control the laser parameters so that you only remove a certain thickness as compared to, say, chemicals where you don't have that much control. So let's look at some of other videos about other methods and compare them. So first of all, we look at sandblasting, then we look at water jet blasting, and then we compare with laser cleaning. So we look at the sandblasting method. So here you see this operator is removing the paint from a ship using sandblasting, and all these contamination is going into the environment. It's pretty noisy, you can hear that. So this was one, and then let's look at the other one, which was here. Yes, so water jet blasting. You see a water jet, this is removing the paint, and again, all the contamination, the rust and the dirt, along with the contaminated water, is going into the environment. Okay, and then finally, let's look at the laser version. So here, using a laser cleaning apparatus, the operator is removing the paint. And you also see this thick tube here. That is a suction pump that basically takes away all the ablated material, so the contamination level is much, much less in the laser method. All right, so now we should talk a little bit about the physics of dependence of laser ablation on material properties and laser parameters. So this is related to how we are choosing different lasers for different applications. So what are important material properties? I've listed them here. Optical attenuation coefficient alpha. So this is related to how deep the beam of light penetrates into the material. So if alpha is large, then it just doesn't penetrate that much. If alpha is small, it could go deeper. So alpha is inversely proportional to the optical penetration depth, L alpha. So L alpha in the units of meter inverse is inversely proportional to the absorption coefficient. The next parameter is thermal diffusivity, dt, in units of millimeters squared per second. And this is defined as thermal conductivity divided by the specific heat and density. So thermal conductivity of material that are like metals are pretty high because they pass the heat very quickly. But other materials such as wood or glass have low thermal conductivity because they don't pass the heat so easily. So thermal diffusivity is related to that. Density is also part of the dt. There's an equation here that shows that dt and density, they are related, inversely proportional to each other. Then there's the heat of vaporization, HV, which is the amount of heat you have to provide to remove a certain mass of the material. So it's given in joules per grams. Okay, so this depends on different material. Now, important laser parameters are type of laser, which defines the wavelength, whether you're working in the IR or mid-IR or UV or visible. Then the pulse width, tau L in seconds. You also have the fluence, which is the energy density in joules per centimeter square, and the beam size, how small the beam is. Of course, the beam size is also related to the fluence, because if the beam size is small, then the fluence will be more. All right, so what we have to understand here is that when the short pulse, when the laser has a short pulse, which is less than 10 picosecond, then the optical penetration depth is similar as thermal penetration depth. So here you see the beam, the orange beam, which is a laser beam, has penetrated into the material, the depth of L alpha. And for pulses that are less than 10 picosecond, the heat is confined to this optical penetration area. So it doesn't go any further. However, when the pulses increase in size to more than 10 picosecond, the heat that is generated goes beyond the optical penetration depth. So it's shown by the yellow color and the depth of LT. So the light actually might go only up to the orange area, but the heat will go in a bigger area defined by this LT, which is the thermal penetration depth. And this thermal penetration depth depends on the pulse width and also depends on the thermal diffusivity. So pulse width come into picture when you are in a regime that is more than 10 picosecond. So to examine this further, we have to define the parameter called fluence threshold, threshold fluence. To achieve ablation, enough energy has to be deposited per unit area to evaporate the material. This fluence, energy per unit area, is called threshold fluence. So when you are in the less than 10 picosecond regime, this threshold fluence only depends on the density of the material, heat of vaporization, and L alpha. This actually has to be alpha, which is the thermal penetration depth. So that this is how you define that. But when you go with pulse widths that are greater than 10 picosecond, the threshold fluence, again, the same two factors, density, heat of vaporization, but you have L tau, which is the thermal penetration depth, as shown there. And this thermal penetration depth depends on the pulse width and also depends on the diffusivity of the material. So therefore, each regime has its own characteristics. So this way, the pulse width come into picture when you have a laser that has a pulse width more than 10 picosecond. So here again, some comparison. Again, jumping back to ablation. You have here a laser with a short pulse and here a laser with a long pulse. And there are differences that you can see. For a short pulse, the femtosecond or short picosecond, you see there is no heat transfer to surrounding material. There's no melt zone. There's no micro cracks, no surface debris, no damage caused to adjacent structures, and it makes a pretty clean cut. And when you have a longer pulse laser, you see there are all kinds of effects that are happening. There's some melting, there is the heat transfer, shock wave, micro cracks, recast layers, surface debris, damage caused by adjacent structures. So all kinds of new effects happens when you use longer pulse. So this is specifically for microfabrication. It shows the difference between the two pulses. So here is an example of three regimes: femtosecond, picosecond, and nanosecond, when you're drilling a hole. And you can see that for the femtosecond, it's so clean cut. And when you go to picosecond, you have debris around, some liquid physics kicks in. And then for nanosecond, the debris becomes even more. So, but for cleaning purposes, like if you want to remove paint, a femtosecond laser is usually low power and they're very expensive, such as a Ti Sapphire laser. They're not suitable. So this is more related to ablation for cutting or drilling, how these different regimes differ from each other. So let's compare a long and short wavelength behavior a little bit more. So CO2 lasers, the long wavelength, they're reflected by metals, but they're absorbed by polymer, and they're suitable for paint removals with metal substrate. So you see in this chart here, let's look at the aluminum, which is right here. So around 1 micron, there is higher absorption, but when you go to higher wavelength, larger wavelength, around 10 micron, there's very low absorption. So if you have a paint or an oxide layer on top of a metal, and you're concerned about the metal substrate, in case of aviation industry, one advantage of using CO2 laser is that it's heavily absorbed by the paint, but is not absorbed that much by the metal. So it's actually reflected by the metal. You can see it has a very small absorption coefficient at around 10 micron. So it doesn't damage the substrate. Now, neodymium YAG laser is suitable for metal cutting. Of course, if you want to cut a metal, it's better to use 1 micron than 10 micron. You have higher absorption. For paint removal over a metal substrate, for a case of aircraft, it may damage the metal substrate unless it's properly focused or the fluence is kept below the damage threshold of the metal. So you have to be careful to control the fluence of the laser so it doesn't damage the metal at the bottom. The advantage of using the near IR over the mid IR is that you could use fiber optics, and it's much more flexible than the mid-IR. Both the near IR and mid-IR, as shown in this right diagram, could be steered. The beams could be steered using galvo drivers and also XY translation stages. So both of them could be steered like that, as shown in here. But the beam of the near IR is much narrower because of the diffraction limit. The beam is much narrower than the mid IR. So that's a difference. Now here is another one, and you see this chart shows ceramic and glass. They have such high absorption at 10 micron. Plastic also, but then when you come to 1 micron, the plastic has very low absorption. Organic material has lower absorption. So there is a trade-off between flexibility of using near IR and also this fact that organic material absorb mid-IR more, but metals reflect mid-IR. You also see there is the excimer lasers. We mentioned that before. Excimer is created under high pressures and certain conditions. A pseudo molecule called excimer is created, which can only exist in an energized state and give rise to laser light in the UV range. And it gives laser radiation by excimer, gives rise to photochemical effects, dissociates chemical bond, and these are some examples. But in this case, you can see krypton fluoride and argon fluoride at 193 and 248 nanometers. They have some absorption for ceramic and glass, but is not as high as the mid IR. Plus that they're very expensive to operate. So this graph shows like what are the suitable lasers that could be chosen based on the application. So one could utilize this graph to decide what laser to choose. Now, applications of laser cleaning, some of them are listed here: cleaning historical monuments, cleaning oxide coatings in semiconductor industry, paint removal in aviation industry, removal of rust from pipes, varnished wood, sandstone, decorative steel, decontamination of nuclear power plant. And I'll go through some of these applications. Here's a chart or a table here that shows you what are the contaminants that could be removed. For example, for oil-based organics, CO2 laser is not suitable. Excimer laser could use oil and grease, but they're very expensive as compared to neodymium YAG. And fiber optics are more available for near IR. So these are some factors that are to be considered. Laser cleaning of historical monuments. You can see 3 examples here. The first one on the left, the obelisk of Pharaoh in Egypt before and after treatment. So you can see that nitrate and sulfate layers have been removed by laser. This most likely has used a near infrared laser to remove these dust and nitrate sulfate layers. Here again, stone cleaning. There's a limestone. On one half has been cleaned, the other half is still dirty. So you can clean with the near IR, focus the beam to a very small spot and take care of all these little details and clean them. And here, marble statue is shown. One side all contaminated, the other side has been cleaned by the laser cleaning. Now, one thing that has to be taken into account is that acid erosion cannot be taken care of by laser cleaning, because if acid erosion has deformed statue, is eaten away, then you can't do anything about it. So here's an example of that. So what are the other advantages of laser cleaning of historical monuments? It's a non-contact method and accurate. Use of fiber optics, no secondary pollution, as in the case of sandblasting, low noise, and basically could remove the nitrate and sulfates, as we mentioned before. Here is a very good application, laser cleaning of aircraft parts. So you can see this aircraft is in the hangar, and there are all these robotics that are around it. They're cleaning different parts of it. So the process has been optimized. So one question that arises is that why can't one paint over the existing paint? So if the paint has been degraded in quality, why cannot just you paint on top of that? And then the answer to that is you add additional weight to the aircraft, which is not desirable. So the old paint has to be removed. Usually before they used to use chemical methods or sandblasting, and then the new layer has to be put on. So CO2 laser is very suitable to do that, as I said, because it doesn't damage the metal substrate, but steering the beam is very difficult. Fiber optic cannot be used. Instead, one can use the near IR version and control the damage threshold to make sure that the metal substrate is not damaged. And it's the laser technique is more environmentally friendly than sandblasting and low noise. We talked about all of that. And it's also faster. Another application is laser cleaning for nuclear decontamination. So after 30 to 40 years, nuclear power plants need to be decommissioned because the parts, including the outside wall, they develop cracks. And there are some areas, such as Ontario, that they generate the electricity using nuclear by a heavy amount. So 60% of electricity generated in Ontario is done through nuclear power plants. So these fission reactors need to be decontaminated after or decommissioned after 30 to 40 years of operation. But you can't just throw the parts out because all these internal parts have been exposed to radioactive material and they need to be cleaned before they are thrown out. And as far as the walls are concerned, there's this scabbling that is required. You can do that using lasers. There's a deposit of cobalt-60 on all the pipes, which is a radioactive material with a half-life of 7 years. And some of these pipes in the nuclear power plant can be cleaned and can be recycled. They're expensive stainless steel. So one can use laser ablation, 10 to 100 kilowatt power in near infrared with the optical fiber delivery to clean these nuclear power plants that are to be decommissioned, and then try to basically recycle the metal parts and dispose of the concrete walls. So let's look at some of the videos of laser cleaning system by Allied Scientific Pro. So I've chosen 3 videos that are very interesting. One is laser cleaning of a stone carved head in Parliament Hill in Ottawa. Then there's a laser cleaning of sandstone flat surface with the Laser Art 100 watts. And then Laser Aero 1000 cleans Boeing aircraft. These are the 3 that I have chosen for. So let's look at these 3. So you can see the beam is a linear beam and is cleaning this historical monument, and it's so narrow. doing a good job in cleaning this head figure. Okay, I think that gives you the idea. Next would be this one, the sandstone. Again, you see that there is a suction pump here, a linear beam that comes out of the galvo. You don't see the galvo, but all the ejected material are taken into this pump, and it's cleaning this surface sandstone very nicely. And then finally, let's look at the cleaning of the Boeing aircraft part. That's the last video. So here the aircraft paint is being removed, and this area by blue has defined where the surface is that has to be cleaned. So that works pretty well in there. Okay, so these videos are there for you to look at. So let's finish with some conclusions. Laser cleaning through the process of laser ablation is more efficient, faster, less noisy, and more economical as compared to other paint removal methods such as sandblasting, dry icing, and chemical stripping. Use of near IR laser with fiber optics makes the paint stripping or contaminant removal very flexible to clean, hard to reach places. Industrial fiber laser are rapidly growing in manufacturing for drilling, scribing, high-speed cutting, paint removal. Laser pulse width, fluence, rep rate, and wavelength are the important parameters that need to be considered for different applications. Material surface properties need to be considered as well, such as thermal diffusivity and penetration depth and absorption, heat of vaporization. Laser cleaning is used extensively in cleaning historical monuments, semiconductor industry, shipping industry, aircraft industry, nuclear decommissioning by removal of paint, rust, and oxide layers. And although CO2 laser wavelength is better absorbed by polymers such as paint and reflected by metals, for paint stripping on metal surfaces, NIR lasers such as fiber lasers can be used as well due to their usage of fiber optics and ability to adjust the laser power to below the damage threshold of metal. So that ends our presentation here. Thank you very much for listening, and I will be glad to answer any questions if there is. You can type your question here, or if you can unmute yourself, you can ask me. I see Mr. Steve Lavoie, the CEO of our company, is attending. If he has any additional comments, he could add. So I will actually write here, are there any questions?
Hi, Rez. This is Steve here.
Yes. Hi, Steve. Go ahead.
Yeah, good. Thanks. Good webinar, Rez. Thank you very much.
Thanks.
Just want to let the people know that we are available. If you guys your question will be available after the webinar, and if you are interested to learn about the price or a possible demonstration, that's something also we can organize. So you can you can contact us at any time. I will be glad to help you out. And if you have also like an application in mind, you can explain here a little bit about the application, and we can comment and tell you if it's a good application for laser. Laser is not for all cleaning application or surface preparation application, but it does quite a bit different kinds of application and stuff. So we'll be glad to give you feedback as well live here. So
Okay, Steve. Also, one of the attendants is asking, what are from HAIC? What are the operation costs of the laser system? This is one question.
yeah, it's a good question. So the nice thing about lasers, like for 100 and 200 watt, they only work with standard 110 volt. So there's no consumable. You just need electricity and you're good to go. And then when we jump to 500 and 1000 watt, then you need a 220 volt to operate the laser. It's a bit more complicated and a bit more costly in terms of power, but it's still, electricity is the main cost.
Okay. Also, Joseph is asking, can laser cleaning replace chemical stripping in its entirety, as in removing a metal-based wear coating from a different parent material, of a parent metal? So
Uh-huh.
I think it can, but if you want to elaborate more on it, Steve?
Yeah, so yeah, chemical is a big issue, especially in aerospace and some other field. There's a lot of regulation coming up. There's a regulation called REACH in Europe that is rolling out, and I think we'll see it in America very very soon. So in some case, laser can clean and you can substitute by laser the chemical, but not in all case. So it's a case by case situation where we need to see what you want in terms of results and what kind of dirt or layer or coating you want to remove. But if the unwanted surface absorb in the laser absorb light in the laser that we are using, then there's a good possibility that it works. So the answer is yes and no. Sometimes it works, sometimes it doesn't work for replacing chemical.
Yes,
So
I think
case
that
by
it
case.
also depends, Steve, on very much on like absorption coefficient for the different metals. If they're close to each other for that particular wavelength of laser, then no. But
Yeah,
if they are different from each other, then the answer is yes. So it boils down to material properties of how these two metals are different as far as the absorption coefficient and heat of vaporization and things
yeah,
that I explained, how they compare.
yeah, exactly. But yeah, we can investigate Richard. I think it was Richard. I think we can investigate this with you if you wish, and we can run some samples for you and try to find the best parameters and give you a clear answer, a yes or no, if it will replace it.
Okay, next question, Steve, is uh, from Rejan. Uh, Number one, he has two questions. We are working on aluminum casting from 1918 German engine. I am
Yeah.
concerned with penetration and physical damage to original casting marks. How do we minimize damage, and how does laser ablation affect magnesium alloy casting? I just want to answer the first one, Steve. You can add to it later, but
Yeah, no
uh,
problem.
I just want to say that for the first one, to minimize damage, you have to carefully choose the damage threshold. We have laser experts at Allied Scientific Pro that could calculate what should be the damage threshold, what should be the laser fluence that does not damage the substrate. So, am I right in that sense, Steve? You have more
Yeah,
experience working with the
yeah,
system.
definitely. And so aluminum casting we're uh,
How,
so
how,
so
how
if
does this?
if he can, if Rejean can elaborate a bit about, maybe this could be done offline, but if we could know what kind of residue from the casting you want to remove. So it must be like a process issue, but if it's kind of a silicon or some oil residue or something, then it's something that we can figure it out with laser, especially for molding, cleaning a mold. When you press mold, or if you do extrusion, we've done some good project on that, and it works really good to remove some kind of a oil residue from the process, the molding process or the extrusion process. So it's something we have some experience with, and we can elaborate maybe after the webinar.
Steve, he says residue is petroleum distillate and sediment and carbon.
Yeah, that should, to my intuition, this should work beautifully, and it doesn't need so much power. So it's a very comfortable application, I think, for laser.
Okay, Alex is asking what kind of profile can be achieved with a 1000-watt system for special coatings? I'm not sure what he means by that. What kind of profile can be achieved with a 1000-watt system for special coating? Can you elaborate a little bit more on it, Alex? What do you mean by profile?
Yeah, we would need to know profile, what it means, and we would need to know coating, what kind of coating. So are we talking like kind of a
You
paint?
have to be more specific, Alex. Need more information.
Yeah, but we can discuss about that. But
Yeah,
maybe it's a beam profile, I think, or
yeah. I would put my email here in case it is in the PowerPoint, but anyone who wants to send a specific question, you can send me and I will forward to the headquarters here. In case,
magnesium. I see the question about magnesium. Magnesium, I'm not too sure. We haven't worked with it, but we did have some requests, and we would be glad to run some tests. Um, Rez, you can also maybe look at the absorption coefficient of magnesium, and we
yes,
we can find this. We can find out quite easily if laser will work for magnesium. But to my intuition, I think it should work. It's like aluminum, and it's even softer than aluminum, if I don't mistaking. So it should work, but it really depends. But we need to try it really.
yeah. I can do some study to see what's the absorption coefficient and properties of.
Yeah, and we can come back to Rajan and give him an answer. So what we will do at the end of the webinar, we'll put all the questions, and then we can put the answers, uh, and then give some more precision on the answers.
Okay.
Okay,
All
so
right. Are there any other questions?
I think that's it for now.
All right. Okay. Thank you very much
Thank
for
you,
listening,
everybody. Bye
and
bye.
thank you Steve, for your comments at the very end. And we will send you this recording, and we'll be glad to follow up with all of you regarding your requests. Thank you. Have a great day. Thank you,
Thank you.
everyone. Bye.
Thank you, Rez.
Thank you, Rez.
Thank you.
Bye.
Thank you so much. Have a good day. Bye.